if we look at the laminar part of the film condensations on a plate and draw the temperature and velocity profile. So let's say this is the condensate and we are looking at the laminar. So we are looking at the laminar film condensation. So in terms of the temperature and velocity profile, if I plot velocity, what you're going to see here is it's going to be zero velocity here, and this is going to be a typical velocity profile, almost reaching to the maximum at the vapor liquid interface, and then going to the vapor phase. So this is going to be the velocity profile. And if I specify this one as the X down direction, and this is Y, and this is the gravity direction. So this is going to be U as a function of Y that we have at any X direction. Similarly, I can plot the temperature profile. So let's say this is the temperature, and the temperature at the surface is Ts. So from certain value of, let's say this is Ts, showing the Ts, the temperature is going to just rise inside that till reaching to the Tsat. So we are, this is going to be temperature profile here. This one is Tsat, and this one represents, just make a color as a base, and this one represents the T of Y in the system. So this is going to be the velocity U and temperature profile. And we have seen for other sort of convections that we need to solve the equations to find the temperature and velocity profiles, and from there we can find H. Now in 1923, Nusselt provided a beautiful analytical analysis, which we can get the convective heat transfer from that analysis. He made a few assumptions. So I'm just gonna write down here. In 1923, we're gonna look at what Nusselt did analysis for this laminar film condensations. So the assumptions that he was making was for this velocity and temperature field. So let's say we have this laminar flow, and the first thing he made was that assuming the surface temperature Ts and the vapor saturation Tsat temperature are going to remain constant. Okay, so analysis, or for doing that, he made some assumptions. One of them is Ts, Tsat remain constant throughout the process, and the other things that he was assuming was the temperature would rise linearly. So see that we have this temperature profile, like the way that he was assuming was that the temperature profile, what we would have is a constant temperature of Tsat, and then we would have a linear rise of the temperature here. So let's say this is Tsat, Ts, and there is this linear profile till we are reaching to Tsat. So temperature profile in the film is going to be linear. That's another assumption. Then another things is he assumed that the heat transfer in this film, in condensate film, is purely conduction. So that was another assumption that he was making. The other one was that there are going to be no shearing stress or no drag forces applied at the liquid vapor interface at the other side of the interface. By that assumptions, what does that mean? Like if I plot the velocity profile here, what I'm going to get is, so let's say in this cross-sectional area, if I plot the velocity profile, it's going to be no slip boundary conditions. And when we say there is no shear stress on the liquid vapor, and the liquid vapor is going to be zero gradient, du dy is going to be zero. So the velocity profile that he was considering was something like that. So here the slope was zero. Oops, actually he was not assuming anything for the other part. So this is going to be u of y, and this is going to be t of y. So I'm just gonna write no shear stress at liquid vapor interface. What does that mean is du dy at delta is zero. So with these assumptions and constant properties, condensate flow is laminar. Okay, laminar. The other assumption was laminar flow and constant properties. Then he took a small element here in the system. So let's say we are looking at the sum delta x. So let's say this is the delta x. And what he was considering here for this delta x was, let's look at this small element. Okay, we know this is delta. Above that is delta, and then he was considering this one as y. So he was taking this small element that I'm just gonna exaggerate here. So let's say that's that small element that I'm taking here. So the top part of this this small element that we have is going to be delta minus y, and that's the part. This is going to be delta x. Now, if you plot the forces that are getting applied to this small element, what we have here is we have weight. So that's the one that's pulling the condensate out under the gravity. And the weight of that one is going to be, this is liquid times g delta minus y. If we assume the other dimension of this plate is b times b d dx. So this is going to be the weight of this element, which is the volume times the density times gravity. And the other things here is there is another force pulling up, like this liquid is replaced by vapor. So we have buoyancy forces. Actually, we have displaced vapor by liquid. So what we have in terms of buoyancy is going to be rho v g delta minus y b dx. Okay, so this volume of liquid is vapor is replaced by liquid, or liquid replaced by vapor. Now another thing here is the shearing force, just holding the liquid on the other side, on the outer side. So they're going to be this shear force, and that shear force is going to be equal to mu L du dy at the location that we are looking at times b dx. Now, if we write the balance of forces, okay, like sigma f equal to 0, so what this means here is weight is going to be equal to viscous shear stress plus the buoyancy force. So it's going to be rho L G y b dx, that's the weight. Viscous is going to be mu L dy. b dx plus rho vg minus y b dx. And from here, we can find an expression for velocity. So du dy would be g rho L minus rho V delta minus Y divided by mu L. So this is going to be the expression for the velocity. Now, if we take the integral of this one, so if we take the integral of this one from at y0 to any y, so it's going to be at u0 to some uy, then we would get an expression for uy, which is going to be g rho L minus rho V divided by mu L y delta minus delta divided by 2. So this is going to give us the distribution of this velocity. So this is going to be this velocity profile that has been assumed for this film condensate. And from the velocity, average of velocity, we can get the mass of that part. So the mass of the condensate at any location of x here, I forgot to put it here, this is y and this is x, at any x can be found by having the velocity profile that we have here, which is going to be average over area of rho of L, density of that, u of y dA. And if we take that integral from y0 to delta for the whole thickness of the condensate at any x location, is going to be rho of L u of y dy, and in fact b dy. Okay, so the area is going to be like the width of the plate times dy that we have, and so that's the integral of that. Yes. If I take the integral of if I replace the velocity profile and take the integral, the mass flow rate is going to be g b rho of L minus rho V delta 3 divided by 3 mu L. So this is going to be the mass flow rates that you're going to have here. Now, if I further extend this one and find out dm dot x over dx, it's going to be gb rho L minus rho V mu L. Delta is going to be a function of x, so I'm going to get delta 2 d delta over dx. Okay. We know that dq, the amount of heat that is getting transferred here from the condensate to the plate is going to be hfg m dot. Okay, oh sorry, dm dot, the minimal amount of the small amount of m that's happening, and it's going to be okay, dm, which is going to be kl b dx tsat minus ts divided by delta. Remember, this is k times area, and this one is the area for the heat transfer for that small element, and this is delta T over L. So this is pure conduction that we are assuming. So this is going to be the dq that is happening here. So we can, from here, if we replace, like from here, we can get dm dot over dx. And if you replace it here in the top equations, then what we are going to have here is delta 3 d delta is going to be equal to mu L KL Tsat minus Ts divided by G rho L rho L minus rho V HFG times dx. And from here, I can get delta x. So I can get the thickness of this film at any location, which will be 4 mu L KL Tsat minus Ts divided by G rho L minus rho V HFG times x to the power of 1 over 4. So this is going to be the thickness of this film at any location. Now we know that the flux at any x is going to be h of that one T sat minus Ts. That's by the Newton's cooling law. And through this is coming from the vapor to the liquid vapor interface, and then from there it's going to be by conduction. So it's going to be KL T sat minus Ts divided by delta. So from here, h of x is going to be KL over delta of x. So I can get an expression for h of x, the heat transfer coefficient, which is going to be G rho L minus rho V HFG divided by 3 mu L T sat minus Ts times x. And if you bring the KL here, it's going to be KL to the power of 3, everything to the power of 1 over 4. Okay, so this is going to be the local heat transfer coefficients at any location of this plate. So let's say this is the plate, and this is the direction of x. At any x, I can find out what is the heat transfer coefficient, and I can find out the heat transfer average hs dx from 0 to L at any length of the system that I want. So at the end of the plate, let's say this is L, is going to be 4 over 3 of h of L. So if I do the replacement and do the math here, I'm going to get 0.943 G rho of L rho L minus rho V HFG KL to the power of 3 divided by mu L T sat minus Ts L 1 over 4. So this is going to be the average heat transfer for a vertical plane. In the laminar regime, which we had the Reynolds number less than 30. So remember that in the laminar regime, the Reynolds delta is going to be less than 30 for this vertical plate, with the assumptions that Nusselt was making to do the analysis.